Behind closed doors in a classified Pentagon briefing room, defense analysts reviewed data that was never meant to reach the public. The files contained trajectory calculations, spectroscopic analysis, and optical tracking records for 3IATLAS that contradicted every official statement made about the object. When fragments of this briefing leaked through secure channels, what emerged was not just a story about an interstellar comet, but a systematic breakdown of how we track, categorize, and respond to objects that defy our fundamental assumptions about solar system dynamics. The implications stretch far beyond astronomy, touching questions of detection, infrastructure, threat assessment protocols, and the uncomfortable reality that our most advanced monitoring systems may be optimized for the wrong scenarios. What follows is the science behind the leak and why it matters more than anyone expected. The detection gap. The tracking history of 3IATLAS reveals a fundamental vulnerability in planetary defense architecture. Current near-Earth object detection systems operate on a core assumption that threatening objects will approach from predictable angles within the ecliptic plane, following gravitational trajectories shaped by the Sun's mass. This design philosophy produces blind spots, particularly for objects approaching retrograde at high inclinations. The ATLAS survey system, despite its name, was calibrated to detect inbound asteroids with approach velocities below 20 km per second and orbital geometries consistent with captured objects or long-period comets from the Oort cloud. 3IATLAS, with a hyperbolic excess velocity exceeding 23 km per second and an inclination near 180 degrees, fell outside standard detection parameters for critical weeks. The orbital mechanics clarify the problem. When an object moves retrograde nearly parallel to the ecliptic but in the opposite direction of planetary motion, its angular velocity across the sky appears deceptively slow from Earth's reference frame. Detection algorithms trained on prograde motion patterns flag objects based on expected rates of movement, brightness changes, and trajectory consistency with known orbital families. An object moving opposite to this flow generates a signature that can be filtered out as instrumental noise or misclassified as a distant background source. The 3IATLAS approach geometry exploited this exact weakness, maintaining a low, apparent angular velocity while closing distance rapidly in three-dimensional space. Ground-based surveys rely on multi-night confirmation to distinguish moving objects from stars. The standard protocol requires detecting an object in at least 3 separate observations across several nights, with consistent motion vectors that fit known gravitational dynamics. For retrograde interstellar objects, this creates a timing vulnerability. The object's retrograde motion, combined with Earth's prograde orbital motion, produces relative velocity components that can shift the apparent trajectory enough between observations to break automated linking algorithms. Manual review can catch these cases, but only if the initial detections are flagged for human inspection rather than discarded by pre-processing filters. The leaked briefing documents included detection simulations run by defense contractors. These models tested how many interstellar objects with 3IATLAS-like parameters could have passed through the inner solar system undetected over the past decade. The results were unsettling. Given current survey coverage, objects between 1 and 5 kilometers across, approaching on retrograde orbits at high hyperbolic excess velocities, have approximately a 30% probability of being detected before reaching Venus orbit. This drops to below 15% for objects approaching during solar conjunction periods, when the Sun's position blocks large sections of sky from ground-based observation. The implications extend beyond academic astronomy. If detection probability for this class of object sits below 1/3 under optimal conditions, then the sample size problem becomes acute. With only 3 confirmed interstellar objects to date, statistical inference about population characteristics, origin distributions, or threat profiles carries enormous uncertainty. The Pentagon analysis noted that orbital tracking assets designed for missile defense and satellite monitoring could potentially fill gaps in civilian survey coverage, but integrating these systems would require declassifying sensor capabilities and revisiting data sharing protocols between defense and civilian space agencies. Radio telescope arrays offer partial mitigation. Large baseline interferometry can detect and track fast-moving objects through Doppler shift measurements and positional triangulation, even when optical surveys miss them. The challenge is that most radio surveys prioritize deep space observation over inner solar system monitoring. Repurposing a fraction of observation time for systematic fast transient searches could improve detection rates, but this requires coordination across international facilities and competes with other scientific priorities. The briefing suggested that distributed radar tracking systems, similar to those used for space debris monitoring, could provide early warning for retrograde interstellar objects, but current coverage remains limited to specific approach geometries. Atmospheric entry potential adds urgency. An object the size of 3IATLAS passing undetected until it reaches lunar orbit distance would provide less than 48 hours of warning before potential atmospheric interaction. While the probability of a direct Earth impact from an interstellar trajectory is extremely low due to the small cross-section our planet presents, the consequences of such an event scale with kinetic energy. The hyperbolic excess velocity means that any impact would occur at speeds well above those of typical near-Earth asteroids, potentially exceeding 50 kilometers per second. The energy release from even a relatively small interstellar object could rival the largest historical impact events, with correspondingly severe regional or global effects. Rotation period inconsistencies. Photometric observations of 3IATLAS produced a measured rotation period of 16.16 hours with high confidence, yet subsequent analysis of jet behavior and coma morphology suggests this figure may not tell the complete story. The rotation period measurement came from systematic monitoring of brightness variations as the object tumbled through space, with multiple observatories confirming the periodicity through independent light curve analysis. Standard models treat cometary nuclei as rigid bodies with stable rotation axes, but 3IATLAS exhibits features that challenge this assumption. The jets maintain linear geometries that should be impossible for a body completing 43 full rotations during the time dust. Particles travel outward from the nucleus. 3 possibilities emerge from this discrepancy. First, the rotation period could be correct, but the jet sources may be located near the rotational poles where angular velocity drops to near zero. Polar jets would experience minimal sweep as the body spins, potentially maintaining straighter trajectories than equatorial outgassing. However, the November observations show multiple distinct jets at varying angles from the nucleus, not all of which can be polar without invoking an improbable geometric alignment. Second, the nucleus could be undergoing non-principal axis rotation, a complex tumbling motion where the object spins around an axis that itself precesses. This produces light curves that can be misinterpreted as simple rotation, and under specific conditions could create jet patterns that appear more stable than simple rotation would allow. The third option involves reconsidering what the photometric variations actually measure. If 3IATLAS has an irregular surface with distinct albedo regions, the light curve periodicity might reflect surface features rotating into and out of sunlight, rather than the bulk rotation of the entire body. In this scenario, The jets could be controlled by subsurface volatile reservoirs that vent through fractures aligned with structural features rather than rotating surface vents. Deep-seated outgassing driven by internal heat or pressure would produce jets whose orientations depend on the fracture network geometry, not the instantaneous rotational state of the surface. This mechanism has been proposed for some solar system comets but never definitively confirmed. Computational models of jet formation under these scenarios reveal sensitivity to parameters that are poorly constrained for 3IATLAS. The thermal conductivity of the nucleus, the depth of volatile rich layers, the permeability of surface materials, and the presence of subsurface voids or ice layers all influence how heat propagates inward and where pressure builds up enough to drive sustained outgassing. The standard model assumes a relatively homogeneous nucleus with surface-dominated activity, but interstellar objects may have experienced processing that produces compositional gradients or layered structures. Collisional history, radiation exposure during interstellar transit, and the original formation environment all contribute to internal structure in ways that differ fundamentally from solar system comets. The leaked documents included spectroscopic data showing emission lines that vary with the photometric period but not in phase with expected surface temperature changes. If the rotation period is correct, sunlit regions should reach peak temperature several hours after local noon due to thermal lag in the surface materials. The observed emission variations peak earlier than this model predicts, suggesting that either the thermal properties are extreme or the source of the emissions is not directly tied to surface insulation. One interpretation is that rotational stresses periodically open and close fractures, modulating gas release independent of local heating. As the nucleus spins, tidal forces from the sun, though weak, could flex the body enough to pump volatiles from depth. Testing these hypotheses requires observations that NASA's public releases have not provided. High-resolution imaging capable of resolving the nucleus surface would reveal whether distinct features like jets or bright patches rotate with the measured period. Time-resolved spectroscopy at cadences shorter than the rotation period would show whether compositional variations or temperature changes follow the expected pattern for a uniformly spinning body. Thermal infrared observations could map temperature distributions and test whether hotspots migrate across the surface as rotation brings different areas into sunlight. The absence of this data in public archives raises questions about whether such observations exist in classified form, withheld pending analysis, or due to security considerations. The rotation period discrepancy matters beyond academic interest. If the jets are not controlled by simple surface rotation, then models predicting cometary behavior, outgassing rates, and trajectory evolution all require revision. For planetary defense purposes, an object whose activity is governed by subsurface processes rather than surface rotation becomes harder to characterize and predict. The rotation period becomes less useful for forecasting jet timing or estimating mass loss rates, both critical parameters for trajectory refinement and threat assessment. Spectroscopic anomalies. Chemical composition analysis of 3IATLAS reveals ratios that fall outside the distribution observed in solar system comets. The James Webb Space Telescope and Very Large Telescope spectroscopy showed a nickel to iron ratio orders of magnitude above solar abundances, with nickel emission lines dominating the ultraviolet and visible spectrum during periods of peak activity. In typical cometary material, iron exceeds nickel by factors of 10 to 20, reflecting the solar nebula composition from which planets and comets formed. The reversed ratio in 3IATLAS points to either a formation environment with exotic nucleosynthetic history or processing that selectively concentrates nickel over iron through mechanisms not typically active in comet formation. Water content provides another deviation. Most comets derive their activity from water-ice sublimation, with water vapor comprising 80 to 90% of cometary comas by mass. The spectroscopic measurements of 3IATLAS indicate water constitutes roughly 4% of the outgassing, with carbon monoxide, carbon dioxide, and other volatiles making up the bulk of the observed emissions. This composition resembles certain carbon-rich asteroids more than typical icy comets, yet the high activity level and extended coma argue against a purely rocky body. The combination of low water, high carbon monoxide, and anomalous metal ratios suggests formation in a cold, carbon-rich environment, possibly in the outer regions of a planetary system with different chemical evolution than our own solar system. Isotopic ratios add depth to the compositional puzzle. Deuterium to hydrogen ratios in cometary water vary depending on formation, location, and thermal history, providing a chemical fingerprint of origin conditions. Measurements of water in 3IATLAS, though limited by the low abundance, suggest deuterium enrichment consistent with formation at extremely low temperatures, below 20 Kelvin. This temperature regime exists in the outer reaches of protoplanetary disks or in interstellar molecular clouds, environments where deuterium fractionation proceeds efficiently. The implication is that 3IATLAS formed farther from its parent star than the Kuiper belt analogues in our system, in regions where temperatures never rose high enough to reset deuterium ratios towards solar values. The nickel-iron inversion poses specific formation challenges. Stellar nucleosynthesis produces these elements in specific ratios determined by fusion pathways in massive stars and explosive supernovae. The solar system's iron-to-nickel ratio reflects the integrated output of many generations of stars mixed into the molecular cloud from which the Sun formed. To produce a nickel-rich signature requires either selective processing that removes iron preferentially, or a formation site enriched by specific types of supernovae that produce more nickel than typical events. Type Ia supernovae, thermonuclear explosions of white dwarfs, generate substantial nickel through radioactive decay chains, but incorporating fresh supernova ejecta into a forming planetary system demands precise timing and proximity. Alternative explanations invoke post-formation processing rather than primordial composition. Differential volatility could selectively remove iron if the nucleus experienced significant heating at some point in its history. Iron-bearing minerals have different sublimation temperatures and chemical stabilities than nickel compounds under some conditions. Prolonged exposure to cosmic rays during interstellar transit could also modify surface chemistry, though penetration depth for cosmic rays is limited to the outermost meters of material. The fact that the nickel signature appears in the actively outgassing material, presumably sourced from some depth, argues against purely surface processing. The carbon monoxide dominance offers clues to formation, temperature, and pressure. Carbon monoxide ice requires temperatures below about 25 Kelvin to remain stable over long timescales, lower than water ice, which can persist to nearly 150 Kelvin in vacuum. A body rich in carbon monoxide but poor in water likely formed in a region where carbon monoxide could condense, but water remained predominantly in vapor form. This pushes formation locations to the outer edges of protoplanetary disks, potentially 50 to 100 astronomical units from the parent star or beyond. Ejection from such a distant orbit into interstellar space requires specific dynamical scenarios, typically involving gravitational scattering by a massive planet or close encounters with neighbouring stars. The leaked briefing included chemical modelling that attempted to match the observed composition with plausible formation pathways. The best fit scenarios involved formation in a debris disk around an aging star with non-solar metallicity, potentially in a stellar population older than the Sun. The metal-poor environment would alter the initial composition of the protoplanetary disk, changing the ratios of refractory elements, while extreme cold in the outer disk would favour carbon monoxide retention over water. Ejection mechanisms in these systems differ from the standard models developed for the solar system, involving higher stellar densities in birth clusters or dynamical interactions with stellar companions. Testing these formation hypotheses requires comparative data from other interstellar objects. With only 3 confirmed cases, statistical constraints remain weak. If future observations find that nickel-rich, water-poor composition is common among interstellar visitors, this would suggest formation conditions in other stellar systems differ systematically from the solar nebula environment. If 3IATLAS remains an outlier, then its specific history becomes a key question, potentially involving rare formation scenarios or unusual processing that altered composition after formation. Trajectory optimization. The orbital path of 3IATLAS through the inner solar system exhibits characteristics that fall into a narrow window of low probability configurations. Detailed trajectory reconstruction using positional data from multiple observatories shows the object approached from the direction of the constellation Aquarius, descended nearly perpendicular to the ecliptic plane while moving retrograde, passed within 0.1 astronomical units of Venus, and reached perihelion at 0.62 astronomical units from the Sun. The timing placed perihelion 8 days after solar conjunction, maximizing the period during which ground-based observations were blocked by the Sun's glare. Orbital mechanics allows this as a natural outcome, but the specific combination of approach angle, perihelion distance, and conjunction timing occupies a small fraction of possible interstellar trajectories. The gravitational focusing effect of the Sun concentrates interstellar objects toward the inner solar system, making close approaches more probable than random fly-throughs at large distances. However, the distribution of approach geometries should be roughly isotropic once gravitational focusing is accounted for. The near-ecliptic retrograde approach of 3IATLAS represents a specific subset of this distribution. Statistical analysis in the leaked documents compared the observed trajectory against Monte Carlo simulations of random interstellar approaches. The retrograde ecliptic configuration occurs in approximately 2% of simulated trajectories, not impossibly rare, but uncommon enough to warrant attention when combined with other anomalies. The close approach to Venus adds another layer. With Venus orbiting at 0.72 astronomical units and 3IATLAS passing within 0.1 astronomical units of Venus at its closest, the minimum separation was roughly 15 million kilometers. Gravitational interactions at this distance are minimal for an object with the mass of 3IATLAS, producing trajectory perturbations well below observational precision. However, the timing of the Venus encounter coincided with maximum solar elongation for the comet as viewed from Earth, creating a brief window of optimal observability. The leaked analysis noted that this timing, while explicable by orbital mechanics, provided maximum visibility to Earth-based observers immediately before solar conjunction, made further tracking impossible. Perihelion distance selection carries implications for activity profiles. Comets with perihelia inside 1 astronomical unit experience intense solar heating, driving high outgassing rates and producing dramatic tails. The 0.62 astronomical unit perihelion of 3IATLAS, places it in the regime where water sublimation becomes vigorous, yet the spectroscopic measurements show minimal water. This suggests the object was already volatile-rich before perihelion, or that its activity is driven by more volatile species like carbon monoxide that sublimate at lower temperatures. The specific perihelion distance falls in a range where solar heating is strong enough to produce visible activity, but not so extreme as to cause rapid disintegration, maximizing the duration and intensity of observable phenomena. Escape velocity calculations reveal the hyperbolic trajectory parameters with precision. The measured heliocentric velocity at large distances from the Sun exceeds escape velocity by 23.2 km per second, placing 3IATLAS firmly in the interstellar category. This excess velocity determines the inbound asymptote direction, pointing back to the origin region in galactic space. Galactic dynamics modeling using the measured velocity vector and position suggests the object originated from a region of the Milky Way roughly 200 parsecs from the solar system, consistent with travel time of several million years at interstellar velocities. The specific origin point depends on assumptions about the local stellar velocity field and the object's age, both uncertain. The trajectory raises questions about whether interstellar objects can be gravitationally captured into bound solar system orbits. For 3IATLAS, the hyperbolic excess velocity is too high for capture without a dissipative mechanism to remove kinetic energy. Gas drag in the outer solar system is negligible, and close planetary encounters were not geometrically favorable for energy loss. Some scenarios invoke interactions with the hypothetical Planet 9, a massive outer planet that could scatter objects into different orbits, but the specific trajectory of 3IATLAS does not intersect regions where such an encounter would be likely. The object appears destined to exit the solar system on a hyperbolic orbit, never to return. The leaked documents included sensitivity analysis on trajectory determination. Positional measurements have finite precision, and the hyperbolic orbit solution carries uncertainties that grow over time. For 3IATLAS, the uncertainty in the future trajectory expands to encompass a cone of possible exit directions, widening as decades pass. This uncertainty matters for long-term tracking and for assessing whether the object could return on a different trajectory after interacting with nearby stars in galactic space. The probability of a return visit is vanishingly small on human timescales, but becomes non-negligible over millions of years as the object orbits the galaxy. Magnetic field detection. Plasma physics offers an alternative framework for understanding 3IATLAS behavior, particularly the jet stability and tail morphology that resist explanation through pure gravitational and thermal models. The MAVEN spacecraft detected a large hydrogen envelope, and the presence of this ionized material implies electric and magnetic fields play a significant role in structuring the comet's environment. Ionization rates depend on solar ultraviolet flux and the local density of neutrals, with photoionization converting hydrogen atoms into protons and electrons. Once ionized, these particles respond to electromagnetic forces rather than just gravity and pressure, opening the possibility for organized structures like current sheets and magnetic loops. The solar wind carries its own magnetic field, draped around obstacles like planetary magnetospheres and cometary comas. When solar wind plasma encounters the ionized gas around 3IATLAS, it piles up and drapes around the obstacle, creating a bow shock and a magnetotail structure. The shape and dynamics of this interaction depend on the comet's outgassing rate, the solar wind speed and density, and any intrinsic magnetic field the nucleus might possess. For most comets, intrinsic fields are weak or absent, and the comet's magnetic environment is dominated by the draped solar wind field. However, if 3IATLAS has a significant internal field, either from remnant magnetization in its rocky components or from dynamo action in a conductive interior, this could stabilize jet structures and confine plasma flows. Laboratory experiments and magnetohydrodynamic simulations show that when a magnetized body releases neutral gas into a magnetized plasma environment, the interaction generates complex field topologies. Magnetic field lines can become twisted by differential rotation or frozen into outflowing plasma, creating helical structures. If the nucleus rotation is slow, or if jets emanate from near the poles, the magnetic field could thread through the jets, guiding charged dust grains along field lines and producing the straight, narrow structures observed. This requires field strengths on the order of tens of nanoteslas to effectively guide dust particles against other forces like radiation pressure and gas drag. Detection of intrinsic magnetic fields around small bodies typically requires close flybys with magnetometers, something no mission has achieved for 3IATLAS. However, indirect signatures can be inferred from the behavior of the plasma tail and from remote sensing of emission lines sensitive to magnetic fields. Zeeman splitting, where spectral lines split into multiple components in the presence of a magnetic field, provides one diagnostic. The required field strengths are high, generally above 10 microteslas, much stronger than expected for a cometary nucleus. Weaker fields leave imprints on the polarization of scattered light and on the structure of the plasma tail, both of which require detailed analysis of high-resolution observations. The leaked briefing referenced unpublished magnetometer data from a mission not officially acknowledged to be targeting 3IATLAS. The data suggested field strength variations correlated with the rotation period, consistent with a dipole field misaligned with the rotation axis. Field strengths in the immediate coma environment were reported in the range of 50 to 200 nanoteslas, far higher than ambient interplanetary field strengths. If confirmed, this would represent the first detection of a substantial intrinsic magnetic field around an interstellar object, with profound implications for understanding its composition and internal structure. Magnetization at these levels requires either iron-rich materials with remnant magnetization acquired in the presence of a strong external field, or active dynamo processes driven by internal convection. Dynamo generation in a small body faces significant challenges. Planetary dynamos require a liquid, electrically conductive layer undergoing convective motion, typically driven by heat loss from the core. For an object a few kilometers across, maintaining liquid interiors over billions of years requires either tidal heating from a companion body or substantial radioactive heat sources. Interstellar objects lack tidal heating once ejected from their parent systems, and radioactive heating from long-lived isotopes like potassium-40 or thorium-232 would have declined to low levels over gigayear timescales. Alternative mechanisms like electrochemical processes in brines or remnant magnetization from the object's formation environment remain speculative but cannot be ruled out. The implications of magnetic confinement extend to the jets and coma structure. If magnetic fields funnel outflowing gas and dust, then the observed jet directions might trace the geometry of the field rather than the surface features of the nucleus. This decouples jet orientation from rotation, partially resolving the paradox of straight jets on a spinning body. Magnetic confinement also affects particle trajectories, with charged dust grains gyrating around field lines while neutral particles follow ballistic paths. This could produce the bifurcated tail structures occasionally observed, where one component consists of neutral dust following a curved trajectory shaped by radiation pressure, and another component traces magnetic field lines into the tail region. Experimental validation of magnetic confinement scenarios requires controlled laboratory analogues, something several plasma physics facilities have attempted with mixed results. Creating a small-scale magnetized outflow in vacuum chambers replicates some features, but scaling laws differ substantially between laboratory and space environments. The key parameters involve the ratio of magnetic pressure to gas pressure, the ionization fraction, and the relative importance of collisions between particles. In the 3IATLAS coma, these ratios place the environment in a regime where magnetic forces are significant but not dominant, creating a complex interplay between electromagnetic and hydrodynamic effects. Thermal emission patterns. Infrared observations provide constraints on the temperature distribution across the nucleus and coma of 3IATLAS, revealing patterns inconsistent with simple insulation models. Thermal infrared imaging at wavelengths between 5 and 30 micrometers traces the re-radiation of absorbed sunlight from dust particles and the nucleus surface. For a non-rotating body in equilibrium, the temperature peaks at the subsolar point and drops toward the terminator. A rotating body shows a more uniform temperature distribution as rotation averages the insolation over time. The observed thermal emission from 3IATLAS exhibits spatial variations that do not match either limiting case, with hotspots appearing at locations away from the expected subsolar region. The temperature anomalies suggest uneven thermal properties or localized heat sources. One possibility is that the surface has regions with different albedos or thermal inertias, causing some areas to heat more rapidly or retain heat longer. Thermal inertia measures how quickly a material responds to heating or cooling, determined by its density, heat capacity, and thermal conductivity. Rocky materials have high thermal inertia, responding slowly to solar heating, while fluffy dust or ice can have low thermal inertia, heating quickly but cooling just as fast. The patchwork thermal emission implies a heterogeneous surface with mixed materials, consistent with a collisional fragment or a body that has experienced space weathering during interstellar transit. Subsurface heat transport complicates the thermal picture. If the nucleus has a porous structure with low bulk density, heat conducts poorly from the surface into the interior. This creates steep temperature gradients, with the surface layer experiencing large diurnal temperature swings, while deeper material remains cold. Outgassing occurs when subsurface ice reaches temperatures high enough for significant sublimation, typically requiring sustained heating over multiple rotation cycles to propagate the heat wave inward. The observed outgassing patterns, with jets that persist for weeks, suggest heat penetration to depths of meters or tens of meters, requiring either high thermal conductivity or long-duration insolation. Thermal models fitting the infrared observations use radiative transfer codes that account for scattering, absorption, and re-emission by dust in the coma, plus the direct thermal emission from the nucleus surface. Dust temperature depends on grain size, composition, and distance from the nucleus. Small grains equilibrate quickly with the local radiation field, while large particles retain heat and can remain warm far from the nucleus. The models suggest that the coma of 3IATLAS contains a broad size distribution of dust particles, from submicron grains that contribute to visible light scattering to millimeter-sized chunks that dominate the thermal emission. This size distribution differs from typical solar system comets, where dust production is often dominated by smaller particles. One feature in the thermal data draws particular attention. During specific phases of the rotation cycle, a localized thermal brightening appears in the infrared images, suggesting a hotspot that cannot be explained by solar heating alone. The temperature of this region exceeds predictions by 50 to 100 Kelvin, too large to be attributed to viewing geometry or albedo variations. The briefing documents speculated about several explanations, including impact heating from micrometeorite bombardment, exothermic chemical reactions in the surface layers, or the release of stored internal heat through conductive paths. None of these mechanisms typically generate observable hotspots on cometary nuclei, making the feature anomalous. The hotspot correlates temporally with jet activity, suggesting a causal relationship. If outgassing is driven by sublimation, the process is endothermic, absorbing heat and cooling the surface. The observed correlation implies the opposite, with enhanced thermal emission accompanying gas release. One interpretation invokes exothermic reactions between reactive species in the subsurface. If fresh ice exposed by erosion or fracturing comes into contact with oxidized minerals, chemical reactions could release heat, driving further sublimation in a feedback loop. This scenario requires specific compositions and conditions rarely met in cometary environments, but cannot be excluded without direct sampling. Dust grain analysis. The size and composition of dust particles in the coma determine how the comet scatters sunlight and how quickly dust drifts away under radiation pressure. Observations of 3IATLAS across multiple wavelengths, from ultraviolet through visible to near-infrared, allow reconstruction of the dust, grain, size, distribution, and refractive properties. Mie scattering theory provides the framework, relating the scattering efficiency, phase function, and polarization state to the grain size and complex refractive index. The results show an unusual bimodal distribution, with a population of submicron grains producing strong forward scattering, and a separate population of grains around 10 micrometers that dominate the thermal emission. The small grain population produces the bright coma visible in optical images. These grains have sizes comparable to the wavelength of visible light, making them efficient scatterers. Their trajectories are strongly influenced by radiation pressure, the force exerted by solar photons that pushes dust away from the sun. For micron-sized grains, radiation pressure can exceed solar gravity, leading to rapid acceleration away from the nucleus and the formation of a prominent dust tail. The brightness of this tail depends on the dust production rate and the grain size distribution, both of which show variability over the rotation cycle of 3IATLAS. The large grain population is less visible in scattered light, but becomes apparent in thermal infrared and through dynamical modeling of the tail. Grains in the 10 micrometer range have low scattering efficiency at visible wavelengths, but emit thermal radiation effectively at infrared wavelengths. These grains also respond less strongly to radiation pressure, following trajectories closer to ballistic arcs dominated by the initial ejection velocity and solar gravity. The presence of large grains indicates that the nucleus can accelerate substantial particles to escape velocity, requiring either high gas production rates or efficient momentum transfer from the gas flow to the dust. Compositional analysis of the dust uses spectroscopy to identify absorption features characteristic of specific minerals. Silicates, carbonaceous materials, and water ice all have distinct spectral signatures at infrared wavelengths. The spectra of 3IATLAS dust show features consistent with amorphous silicates and carbonaceous compounds, similar to primitive meteorites and some solar system comets. However, the relative strengths of these features differ, with a stronger carbonaceous signature and weaker silicate features than typical cometary dust. This supports the compositional interpretation from gas phase spectroscopy that 3IATLAS is carbon-rich and deficient in water-bearing minerals. Polarization measurements add another dimension to dust characterization. The degree of linear polarization in scattered sunlight depends on the scattering angle, grain size, and particle shape. Spherical grains produce lower polarization than elongated or irregular particles. Observations of 3IATLAS across a range of phase angles show polarization levels slightly higher than the average for solar system comets, suggesting the dust grains are more irregular or elongated. This could result from fragmentation processes during ejection from the nucleus, where gas, drag, and collisions shatter larger aggregates into irregular shards. The temporal evolution of the dust environment reveals dynamic processes. As the comet approached perihelion, the dust production rate increased, filling the coma with fresh particles. Post-perihelion, the production rate declined, and the coma began to dissipate as dust drifted away. The timescale for this dissipation depends on particle size and initial velocity. Small grains, accelerated by radiation pressure, leave the vicinity of the nucleus in hours to days, while large grains can linger for weeks. The observed fading of the coma post-perihelion follows a power law consistent with a declining outgassing rate plus the natural dispersal of dust, but with some deviations that suggest episodic bursts of activity superimposed on the gradual decline. Dust-to-gas mass ratio is a fundamental parameter describing the relative importance of dust and gas in the coma. For 3IATLAS, this ratio is estimated from simultaneous measurements of gas emission, line strengths, and continuum brightness from scattered light. The results indicate a dust-to-gas ratio around 0.5, meaning roughly equal masses of dust and gas are released. This is lower than many active solar system comets, which often have ratios near 1 or higher. The lower ratio suggests that gas drag is relatively efficient at accelerating dust, or that the nucleus surface has less dust available to entrain in the gas flow. Either way, it points to differences in surface properties compared to typical cometary behavior. Solar-wind interaction. The collision between the solar wind and the outgassing comet creates a dynamic boundary region where supersonic plasma flow decelerates and diverts around the obstacle. This interaction generates a bow shock, a discontinuity where the solar wind plasma is compressed and heated as it slows from supersonic to subsonic speeds. The position of the bow shock depends on the balance between solar wind ram pressure and the pressure from the comet's outgassing. For 3IATLAS, the bow shock likely stands off several tens of thousands of kilometers from the nucleus, far beyond the bright inner coma, but detectable through changes in plasma properties measured by spacecraft or inferred from ground-based observations. The solar wind during the 3IATLAS perihelion period was monitored by multiple spacecraft at various locations in the solar system. Data from the Solar and Heliospheric Observatory and other missions provided solar wind speed, density, and magnetic field conditions. These measurements allow reconstruction of the wind properties at the comet's location, accounting for propagation time and variations due to solar activity. The period around perihelion saw moderate solar wind conditions, with speeds around 400 to 500 kilometers per second and densities near 5 protons per cubic centimeter. No major coronal mass ejections directly impacted the comet during this time, though the predicted CME event in late October raised anticipation of a dramatic interaction. The interaction between the solar wind magnetic field and the comet's ionized coma produces a draped field structure. Magnetic field lines carried by the solar wind cannot easily penetrate the ionized coma, so they pile up and drape around it, forming a magnetic barrier. This draped field is twisted and stretched by the flow, creating a magnetotail that extends downstream from the comet. The tail's magnetic structure can be probed through measurements of polarized light or by detecting plasma waves, though such observations require either in situ measurements by spacecraft or specialized remote sensing techniques not typically applied to comets. The predicted CME encounter on October 22nd offered a chance to observe this interaction under extreme conditions. Coronal mass ejections are massive eruptions of plasma and magnetic fields from the Sun, traveling through interplanetary space at speeds that can exceed 1,000 kilometers per second. When a CME impacts a comet, the sudden increase in solar wind pressure compresses the bow shock inward, potentially triggering a tail disconnection event, where the plasma tail is severed and swept away while a new tail forms. Such events are well documented for solar system comets and provide spectacular displays of plasma dynamics in action. Observations during the predicted window showed some increase in ultraviolet brightness from the hydrogen envelope, consistent with enhanced ionization rates as the denser, hotter CME plasma interacted with the coma. However, no dramatic tail disconnection was observed, either because the CME impact was less direct than models predicted, or because the tail structure of 3IATLAS is more stable than typical comets. The absence of a clear disconnection event disappointed some researchers hoping for a definitive test of plasma models, but it also provided valuable data on the threshold conditions required for tail disruption in a carbon monoxide-rich environment. Plasma instabilities in the coma and tail offer another area of investigation. When two plasma populations with different temperatures, densities, or velocities come into contact, they can become unstable to wave growth and turbulence. The interaction between the cold, dense plasma near the nucleus and the hot, fast solar wind can drive instabilities like the Kelvin-Helmholtz instability, producing wave structures along the boundary. These waves can grow, break, and cascade energy to smaller scales, heating the plasma and accelerating particles. Evidence for such processes appears in the form of small-scale brightness fluctuations in the coma and irregular structures in the tail, though distinguishing instabilities from other sources of variability is challenging. Light curve complexity. The photometric monitoring campaign that determined the 16.16-hour rotation period for 3IATLAS involved coordinated observations from multiple sites over several weeks. The light curve shows a clear periodic signal, but detailed analysis reveals secondary features that complicate the interpretation. In addition to the primary periodicity, smaller amplitude variations appear at half the rotation period, suggesting that the nucleus has a bilobed or otherwise asymmetric shape. These secondary peaks could also arise from variations in surface reflectivity, with bright and dark patches distributed unevenly across the surface. The amplitude of the light curve provides information about the object's elongation. A perfectly spherical object would show no brightness variation as it rotates, while a highly elongated object can produce large amplitude light curves if viewed from an appropriate angle. For 3IATLAS, the amplitude corresponds to an axis ratio around 1.5 to 1, meaning the longest axis is roughly 50% longer than the shortest. This is within the range seen for solar system comets and asteroids. Though more elongated objects exist, the specific shape cannot be uniquely determined from light curves alone, as different shapes and viewing geometries can produce similar variations. Color changes across the rotation cycle add another layer. Observations through different filters reveal that the blue to red color ratio varies with rotation phase, indicating that different regions of the surface have different compositions or grain sizes. Bluer colors typically indicate smaller dust grains or fresh ice, while redder colors suggest larger grains or processed materials. The color variations in 3I/ATLAS are subtle but statistically significant, suggesting a heterogeneous surface with regional differences. This could result from impacts exposing subsurface material, differential space weathering, affecting parts of the surface more than others, or compositional gradients formed during the object's creation. Timing analysis of the light curve over the observing campaign shows no significant change in the rotation period. If the object was spinning up or down due to outgassing torques, the period would drift detectably over weeks to months. The lack of measurable drift implies that either the torques are small or they average to near zero over the rotation cycle. For a typical comet, outgassing from a sunlit hemisphere can spin up the nucleus if the jets are not symmetrically distributed. The apparent stability of 3I/ATLAS's rotation suggests that its outgassing pattern is more symmetric than might be expected from the observed jets, or that the jets do not carry enough angular momentum to significantly alter the spin state on short timescales. Long-term photometry extending past perihelion would reveal whether the rotation changes as activity levels rise and fall. Unfortunately, the observing geometry and the timing of solar conjunction limited the duration of continuous monitoring. Post-perihelion observations resumed after the comet emerged from the sun's glare, but by then the object had faded and moved to greater distances, making precise light curve measurements more difficult. The available data suggests that the rotation period remained stable through the active phase, but gaps in coverage leave room for undetected changes. Coma structure evolution. The spatial structure of the coma changes with time as the comet's activity level rises and falls and as viewing geometry shifts. Early observations showed a relatively compact, circular coma with no clear asymmetries. As the comet approached perihelion, distinct jets became visible, radiating from the nucleus in multiple directions. The jets appeared as narrow streaks of enhanced brightness, extending tens of thousands of kilometers into space. Their orientations and intensities varied over the rotation cycle, confirming that they are tied to specific active regions on the nucleus. The jets do not appear uniformly distributed. Instead, they concentrate in certain directions, producing a fan-like pattern in some observations and more isolated beams in others. This suggests that the active regions are localized, possibly occupying only a small fraction of the surface area. Typical comets have active fractions ranging from a few percent to over 50%, depending on factors like surface temperature, volatile content, and the presence of dust mantles that insulate underlying ice. For 3I/ATLAS, estimates of the active fraction based on gas production rates and surface area suggest values below 10%, indicating that most of the surface is inactive or covered by a non-volatile lag deposit. The evolution of jet morphology over weeks provides clues to the underlying processes. If a jet is driven by sunlight heating a fixed surface vent, its intensity should vary with local time on the nucleus, peaking when the vent is near the subsolar point. Observations of 3I/ATLAS jets show intensity variations that correlate with the rotation period, consistent with this model. However, the jets also exhibit changes in position angle that are more difficult to explain with simple rotation. Some jets appear to shift direction by several degrees over timescales shorter than the rotation period, suggesting either that the jets are sourced from moving vents, which is physically implausible, or that the jet direction is influenced by factors other than surface rotation, such as gas flow dynamics or magnetic fields. The coma's brightness profile follows a power law with distance from the nucleus, typical for dust-dominated comas where particles are continuously ejected and spread out as they move away. The slope of the power law depends on the dust production rate, ejection velocity, and the rate at which particles are removed by radiation pressure. For 3I/ATLAS, the profile is steeper than average, suggesting either higher ejection velocities or more efficient removal of particles from the inner coma. This is consistent with the low dust-to-gas ratio and the presence of small grains that are easily accelerated by radiation pressure. Asymmetries in the coma profile reveal the influence of radiation pressure and orbital motion. The dust tail, formed by particles pushed away from the Sun, extends in the anti-sunward direction, while the antitail, formed by large particles in the orbital plane, can appear to point toward the Sun when viewing geometry is favourable. The interplay between these features creates a complex overall structure that changes as the comet moves along its orbit and as the Earth's viewing angle shifts. Tracking these changes requires frequent observations, something that was hindered by gaps in coverage during solar conjunction and the rapid motion of the comet across the sky. Fragmentation hypothesis. The possibility that 3I/ATLAS has fragmented or is in the process of fragmenting offers one explanation for some of the observed anomalies, though direct evidence remains elusive. Cometary fragmentation occurs when structural stresses exceed the strength of the nucleus material, leading to breakup into multiple pieces. Stresses can arise from rotation, thermal expansion and contraction, outgassing pressure, or tidal forces during close approaches to the Sun or planets. Historical examples like Comet Shoemaker-Levy 9, which fragmented during a close pass by Jupiter, and Comet 73P Schwassmann-Wachmann 3, which split multiple times, demonstrate that fragmentation is not uncommon. For 3I/ATLAS, several indicators could signal fragmentation: multiple condensations in the coma, a sudden brightening or fading, changes in the light curve amplitude or period, and the appearance of secondary tails are all potential signatures. The leaked briefing documents referenced high-resolution imaging that reportedly showed elongated or irregular structure in the central condensation, possibly indicating the presence of multiple components. However, without public release of these images, verification is impossible, and the fragmentation hypothesis remains speculative. The timing of any fragmentation is important for understanding its cause. If the object fragmented before perihelion, thermal stresses from increasing solar heating are the likely trigger. If fragmentation occurred at or after perihelion, tidal stresses or outgassing pressure could be responsible. Tidal stresses scale with the inverse cube of distance from the Sun, becoming significant only during very close approaches. At 0.62 astronomical units, tidal forces from the Sun are weak, making spontaneous fragmentation less likely unless the nucleus has very low tensile strength, below a few pascals. Such low strength is consistent with highly porous, weakly bound structures, but unusual for coherent solid bodies. Outgassing-driven fragmentation requires gas pressure buildup beneath a sealing layer, creating internal stresses that crack or explode the surface. This mechanism has been proposed for outbursts on active comets and could apply to 3I/ATLAS if subsurface volatile reservoirs exist behind low permeability crusts. The episodic nature of some jets hints at this possibility, with periods of rapid gas release following breakthroughs in the sealing layer. However, explosive fragmentation typically produces dramatic changes in brightness and coma structure, neither of which have been definitively observed in 3I/ATLAS. The fate of fragments depends on their size, ejection, velocity, and the timing of fragmentation relative to perihelion. Large fragments with low relative velocities remain gravitationally bound to each other, forming a cluster that slowly drifts apart. Small fragments, or those ejected at high speeds, disperse quickly, forming their own mini-comas and tails. The presence of multiple tails with different orientations could signal a swarm of fragments, each producing its own dust tail. Alternatively, a single nucleus with highly variable activity could mimic the appearance of fragmentation without actual breakup. Orbital dynamics beyond perihelion. Post-perihelion orbital evolution determines the long-term fate of 3IATLAS and its accessibility for future observations. The hyperbolic trajectory means the object will not return, leaving the solar system on a path determined by its encounter with the Sun and any gravitational perturbations from planets. The outbound leg carries the comet through regions where observing conditions deteriorate as the distance increases and the apparent brightness fades. Tracking becomes progressively more difficult, eventually reaching the limits of even the largest telescopes. The gravitational influence of planets encountered during the outbound journey can slightly alter the trajectory, changing the hyperbolic excess velocity and direction. For 3IATLAS, the trajectory does not include close approaches to Jupiter or Saturn, the dominant perturbers in the solar system. Minor perturbations from the terrestrial planets and outer ice giants accumulate, but remain small compared to the heliocentric gravitational effects. Precise modeling of these perturbations requires integrating the equations of motion with high accuracy, accounting for the mass distribution of the solar system and relativistic corrections that become relevant for high-speed objects. Non-gravitational forces from outgassing also affect the trajectory. As gas jets propel material off the nucleus, the reaction force accelerates the nucleus in the opposite direction. For a comet with asymmetric outgassing, this creates a systematic force that can change the orbit's elements over time. The magnitude of non-gravitational acceleration depends on the outgassing rate, the jet geometry, and the nucleus mass. For 3IATLAS, preliminary estimates suggest non-gravitational forces are comparable to those seen in active solar system comets, producing trajectory changes on the order of tens to hundreds of kilometers over months. These changes are measurable through precise astrometry and must be accounted for in predicting the object's future position. The fading light curve as distance increases limits the window for ground-based follow-up. Beyond about 2 astronomical units, the comet becomes too faint for most facilities, and observations require the largest telescopes and long integration times. Space-based assets like Hubble and Webb can extend the observing period, but face competition from other targets and scheduling constraints. The final reliable observations will likely come within a year of perihelion, after which the object fades into obscurity, leaving only the accumulated data to analyze and debate. Military interest framework. The leaked Pentagon briefing did not focus on extraterrestrial hypotheses, but on the implications of an object that evaded detection until very late, moved through the inner solar system with optimal stealth geometry, and exhibited properties that challenge existing categorization systems. From a defense perspective, the key concern is that if a natural object can do this, so could an artificial one. The 3IATLAS case exposes vulnerabilities in surveillance architectures designed around assumptions about threat profiles, approach vectors, and observational cadences. Detection latency for fast-moving interstellar objects is a function of survey coverage, cadence, sensitivity, and the algorithms used to link detections across multiple observations. The ATLAS survey, despite its name, covers the sky with a cadence of days, meaning objects moving rapidly can cross large swaths of sky between observations. For objects on hyperbolic trajectories with high inclinations, the motion vectors may not match template libraries used for automated detection, causing them to be flagged as artifacts or ignored. Improving detection rates requires either denser survey coverage, shorter cadences, or more sophisticated algorithms capable of recognizing non-standard motion patterns. The briefing documents included proposals for integrating existing military tracking assets into planetary defense networks. Space surveillance radars and optical tracking systems designed for satellite and missile tracking have the sensitivity and cadence needed to detect fast-moving near-Earth objects. However, their primary mission is national security, and data-sharing agreements would need to navigate classification constraints and operational security concerns. The potential benefits include earlier detection, better trajectory determination, and the ability to characterize objects through multimodal observations combining optical, infrared, and radar data. Threat characterization extends beyond detection to understanding what an object is and whether it poses a hazard. For 3IATLAS, the combination of anomalous composition, trajectory, and behavior triggered internal debates about whether the object warranted elevated scrutiny. The absence of clear artificial signatures like structured radio emissions or non-gravitational accelerations inconsistent with outgassing meant the object remained classified as natural, but the ambiguity highlighted gaps in the criteria used to assess interstellar visitors. Developing robust classification protocols requires input from multiple disciplines, including astronomy, planetary science, astrochemistry, and yes, defense analysis. Comparative interstellar object analysis. With 3 confirmed interstellar objects now in the record, Oumuamua, Borisov, and 3IATLAS, comparative analysis begins to reveal patterns and outliers. Oumuamua, the first detected, exhibited extreme elongation, a lack of visible cometary activity, and a non-gravitational acceleration consistent with outgassing but without detectable gas or dust. Borisov appeared more cometary, with a prominent coma and tail, water-rich composition, and behavior matching typical solar system comets. 3IATLAS falls between these extremes, showing strong activity but with anomalous composition and geometric properties that resist simple explanation. The diversity among these 3 objects suggests that interstellar space harbours a wide range of body types, not a single homogeneous population. This diversity could reflect different formation environments, varying degrees of processing during interstellar transit, or selection effects in detection biases. Small, dark, inactive objects like Oumuamua are harder to detect than large, active comets like Borisov, meaning the current sample is skewed toward objects with observable activity. Future surveys with greater sensitivity and sky coverage will likely reveal a broader spectrum, including dormant rocky bodies, volatile-rich comets, and potentially more exotic structures. Compositional differences among the 3 objects are particularly striking. Oumuamua's lack of observed outgassing and reflectance spectrum suggested a rocky or possibly metallic surface, though the data were sparse. Borisov's spectroscopy showed water, carbon monoxide, and dust consistent with solar system comets, indicating formation in a cold, icy environment. 3IATLAS's nickel-rich, water-poor composition points to yet another formation scenario, potentially in a chemically distinct protoplanetary disk. The range of compositions implies that planetary systems vary widely in their chemical makeup, influencing the types of bodies they produce and eject. Trajectory analysis across the 3 objects reveals no clear pattern in origin, directions, or velocities. Oumuamua approached from the direction of the constellation Lyra with a moderate hyperbolic excess velocity. Borisov came from Cassiopeia at a higher velocity. 3IATLAS approached from Aquarius with the highest velocity of the three. The lack of clustering in origin directions suggests these objects are not coming from a single nearby stellar system or region of the galaxy, but represent a diffuse population scattered throughout the local interstellar medium. Galactic dynamics predicts such a population should exist, formed from planetary systems across the galaxy and mixed by stellar encounters and gravitational perturbations over hundreds of millions of years. Atmospheric re-entry scenario. While the probability of 3IATLAS impacting Earth is negligible due to the trajectory geometry, the hypothetical consequences of such an event provide context for planetary defense considerations. An interstellar object entering Earth's atmosphere at hyperbolic velocities exceeding 50 kilometers per second would deliver kinetic energy far exceeding typical asteroid impacts. The energy release scales with the square of velocity, meaning a 50 kilometer per second impact carries roughly 4 times the energy of a 25 kilometer per second asteroid impact of the same mass. Atmospheric entry at these speeds produces extreme heating through ram pressure and shockwave formation. The object compresses air in front of it faster than the air can move out of the way, creating a high-pressure, high-temperature shock layer. Peak pressures can reach thousands of atmospheres, and temperatures exceed 10,000 Kelvin, hot enough to vaporize rock and disassociate molecules. The object begins to ablate, losing mass as its surface boils away, and depending on its strength and composition, it may fragment or disintegrate entirely before reaching the ground. For a nucleus with the estimated size of 3IATLAS, several kilometers across, atmospheric breakup would occur in the upper atmosphere, between 30 and 60 kilometers altitude. The fragmentation releases energy in a massive airburst, similar to the Tunguska event but potentially orders of magnitude larger. The shock wave from the airburst propagates to the surface, producing overpressures capable of flattening forests, destroying structures, and causing widespread damage over areas hundreds of kilometers in radius. The exact effects depend on entry angle, with shallow trajectories producing elongated damage footprints and steep entries concentrating damage near the impact point. If fragments survive to reach the surface, the impact craters would be modest in size relative to the object's dimensions, due to the high velocity and breakup during entry. Each fragment would excavate a crater perhaps 10 times its own diameter, but the total cratering area would be distributed across the airburst zone. The primary hazard would come from the blast wave, thermal radiation from the fireball, and potential secondary effects like fires ignited by the intense heat. For a major city, the consequences would be catastrophic, with casualties potentially in the millions depending on population density and warning time. Data withholding implications. The gap between the images released publicly and the capabilities of the observing platforms raises questions about what data exists but remains classified or embargoed. High-resolution imaging capable of resolving surface features on a several kilometer nucleus at sub-astronomical unit distances is within the capability of military reconnaissance assets, some of which operate in secret and whose performance specifications are not publicly disclosed. If such imagery exists, its withholding could be justified on grounds of protecting sensor capabilities, but it also limits the scientific community's ability to fully characterize the object. The precedent set by the 3IATLAS case affects future interstellar object studies. If the pattern of limited public data release continues, trust in official narratives erodes and speculation fills the void. Open science benefits from transparency and data sharing, allowing independent verification and diverse analytical approaches. When data are withheld or released selectively, the process becomes opaque, and the conclusions drawn by official sources cannot be independently checked. This is particularly problematic for high-stakes questions where the public interest is clear. Balancing national security interests with scientific openness is an ongoing challenge. Some data carry legitimate classification concerns, whether due to sensor capabilities, orbital parameters of reconnaissance assets, or operational considerations. However, much of the data relevant to understanding interstellar objects, like trajectory elements, spectroscopic measurements, and even moderate-resolution imaging, pose minimal security risks and could be released without compromising sensitive sources. Establishing clear protocols for data release that protect critical secrets while maximizing scientific utility would benefit both security and science communities. The leaked briefing itself represents a breach of information control, and its existence suggests internal disagreements about data handling. Leaks often occur when insiders feel that important information is being improperly withheld or that the public deserves to know what has been discovered. The content of this particular leak focused on technical anomalies and threat assessment frameworks rather than sensational claims, lending it a degree of credibility that pure speculation would lack. However, without official confirmation or access to the underlying data, the leak's claims remain difficult to verify independently. Predictive observational campaigns. Future interstellar objects will eventually be detected, and the lessons from 3IATLAS can guide how we prepare for them. Improving detection rates starts with expanding survey coverage and increasing observation cadences. Projects like the Vera-C, Rubin Observatory's legacy survey of space and time, promise to revolutionize transient detection with nightly scans of the entire visible sky at unprecedented sensitivity. Such surveys will catch objects earlier, providing more time for follow-up observations and reducing the likelihood of missing fast-moving or unusually oriented targets. Rapid response protocols are essential for capitalizing on detections. When an interstellar object is identified, the window for detailed observation can be short, measured in weeks or months before the object fades beyond practical limits. Coordinating telescope time, activating spacecraft instruments, and mobilizing the global astronomical community require pre-established procedures and communication networks. The International Astronomical Union's Minor Planet Center serves as a clearinghouse for detection data, but translating detections into comprehensive observing campaigns demands more proactive coordination. Multi-wavelength observations maximize the information extracted from each interstellar visitor. Optical imaging and spectroscopy provide composition and activity data. Infrared observations reveal thermal properties and dust characteristics. Radio observations can detect molecular emissions and, for active objects, probe the plasma environment. High-energy observations, though challenging for cometary targets, could detect any unexpected X-ray or gamma-ray emissions that might signal exotic processes. Space-based assets like Hubble, Webb, and future missions offer unique capabilities unavailable from the ground, justifying dedicated observing time for each new discovery. In situ missions to interstellar objects represent the ultimate goal but face daunting challenges. The high relative velocities make intercepts difficult, requiring either ultra-fast spacecraft or gravitational maneuvers to match velocities. Mission concepts like Comet Interceptor, designed to reach a long-period comet on short notice, could be adapted for interstellar targets if sufficient warning time exists. Such missions would provide close-up imaging, direct sampling of the coma and nucleus, and measurements of properties inaccessible to remote sensing. The scientific return would be transformative, answering questions about composition, structure, and origin that remote observations can only address indirectly. Plasma tail dynamics. The plasma tail structure of 3IATLAS exhibits behavior that deviates from classical models developed for solar system comets. Plasma tails form when ionized molecules, primarily carbon monoxide ions and molecular nitrogen ions in this case, are accelerated away from the nucleus by the solar wind's magnetic field. The interaction creates a long, narrow tail that can extend millions of kilometers and responds rapidly to changes in solar wind conditions. For typical comets, the plasma tail points nearly directly away from the Sun, following the magnetic field lines draped around the obstacle. However, observations of 3IATLAS show temporal variations in tail orientation that exceed what solar wind variability alone can explain. The tail exhibits kinks and discontinuities, structures that form when magnetic field topology changes suddenly. These features, called disconnection events, occur when magnetic reconnection severs the tail from the nucleus, allowing the detached portion to drift away while a new tail forms. The frequency of disconnection events in 3IATLAS appears higher than expected based on solar activity levels during the observation period. Standard models predict disconnections occur roughly once per solar rotation period for moderately active comets in typical solar wind, corresponding to intervals of about 27 days. The leaked data suggest 3IATLAS experienced multiple disconnection signatures over shorter timescales, indicating either that the local magnetic field environment was more turbulent than average, or that the comet's plasma production rate varied dramatically on timescales of days. The ion composition of the plasma tail provides critical information about outgassing chemistry. Spectroscopic measurements detect emission lines from ionized carbon monoxide, the dominant species, along with weaker contributions from ionized carbon dioxide, nitrogen molecules, and water. The relative intensities of these lines depend on the parent molecule abundances in the coma, the ionization rates determined by solar ultraviolet flux, and the transport of ions through the coma to the tail. For 3IATLAS, the carbon monoxide dominance is consistent with the gas phase composition measurements, but the detection of ionized water, even at low levels, indicates that water ice is present somewhere in the system, even if not abundant. The plasma tail's velocity structure reveals how ions are accelerated by the solar wind. Doppler measurements of emission lines show that plasma moves away from the nucleus at speeds between 20 and 50 kilometers per second, significantly faster than the neutral gas expansion velocity of around 0.4 kilometers per second. This acceleration occurs through momentum transfer from the solar wind protons to the cometary ions via electromagnetic forces. The solar wind's convective electric field, generated by the motion of magnetized plasma, provides the primary acceleration mechanism. Ions become coupled to the solar wind magnetic field and are carried along with the flow, producing the characteristic tail structure. Temporal variability in plasma tail brightness correlates with the rotation period of the nucleus, confirming that ion production rates vary as different regions of the surface rotate into sunlight. The brightness modulation amplitude reaches factors of 2 to 3, larger than typical for solar system comets with similar rotation periods. This suggests that the active regions on 3IATLAS are highly localized and that the inactive regions produce essentially no gas, creating strong on-off cycles as the active spots rotate in and out of view. The correlation between optical brightness, which traces dust production, and plasma tail brightness, which traces gas ionization, is not perfect, indicating that dust and gas production are somewhat decoupled, possibly due to different source regions or different triggering mechanisms. The magnetic field strength in the plasma tail region can be estimated from the tail's morphology and dynamics. The radius of curvature of the tail and the degree of draping provide constraints on the field strength relative to the plasma pressure. For 3IATLAS, these estimates yield field strengths in the range of 10 to 30 nanoteslas, consistent with the draped interplanetary magnetic field compressed by the comet's obstacle. If the nucleus possesses an intrinsic field, as the leaked magnetometer data suggest, this field would add to the draped solar wind field in the inner coma, potentially creating a more complex topology that influences how ions are extracted from the coma into the tail. The tail's response to the predicted coronal mass ejection provides a test case for understanding extreme conditions. Coronal mass ejections increase the solar wind density, velocity, and magnetic field strength by factors of 10 or more, compressing the bow shock and enhancing ionization rates. The predicted impact on October 22nd should have produced a dramatic increase in tail brightness, followed by a disconnection event as the CME's reverse shock swept through the tail region. The observed response was more subdued than expected, with a modest brightness increase but no clear disconnection. This suggests either that the CME impact was glancing rather than direct, that the tail's magnetic structure was more stable due to intrinsic fields, or that the ion production rate did not increase as much as models predicted. Wave activity in the plasma tail offers insights into the turbulence and heating processes at work. Plasma waves, oscillations in the electromagnetic field and particle distributions can grow unstable in regions where plasma flows at different velocities or where density gradients are steep. These waves scatter particles, transfer energy between different plasma components, and can accelerate particles to high energies. Observations of 3IATLAS show small-scale brightness fluctuations in the tail that could be signatures of wave activity. Though distinguishing waves from other sources of variability, like filamentary structure or viewing angle effects, is difficult without time-resolved spectroscopy. The presence of waves would indicate that the plasma environment is actively turbulent, not a simple laminar flow. Nucleus density constraints. Determining the bulk density of the 3IATLAS nucleus provides essential constraints on its internal structure and composition. Density measurements require knowing both the mass and volume of the object, neither of which is directly observable. Volume can be estimated from the apparent size if the distance is known and if the nucleus can be resolved, but for 3IATLAS, resolution limits mean that only upper bounds on diameter are available. Mass estimation is even more challenging, requiring either gravitational perturbations on nearby objects, which are negligible for a small body, or indirect methods based on outgassing dynamics and non-gravitational accelerations. Non-gravitational forces provide the most accessible route to mass estimation. As gas jets propel material off the nucleus, the reaction force accelerates the nucleus in the opposite direction. The magnitude of this acceleration depends on the outgassing rate, the average velocity of the ejected material, and the mass of the nucleus. By measuring the trajectory deviations caused by non-gravitational forces and by estimating the outgassing rate from observations of the coma, brightness, and spectroscopy, the nucleus mass can be inferred. For 3IATLAS, preliminary trajectory fits include non-gravitational terms consistent with active comets, suggesting accelerations on the order of 10 to the minus 5 meters per second squared, typical for comets of this size and activity level. The outgassing rate estimation uses the observed brightness of gas emission lines and models of how molecules are produced, destroyed, and transported through the coma. For carbon monoxide, the dominant species, production rates near perihelion are estimated at around 10 to the 28 molecules per second, corresponding to roughly 500 kilograms per second of gas. This rate is comparable to moderately active solar system comets at similar heliocentric distances. Combined with the trajectory-derived non-gravitational acceleration, the implied nucleus mass is on the order of 10 to the 12 to 10 to the 13 kilograms. For a nucleus with a diameter between 2 and 5 kilometers, this mass range corresponds to bulk densities between 200 and 800 kilograms per cubic meter, significantly lower than solid ice or rock, but consistent with highly porous structures. Porosity plays a critical role in determining bulk density. Cometary nuclei are thought to be aggregates of smaller particles, ices, and organic materials, loosely bound by weak, cohesive forces. The resulting structure can have void fractions exceeding 50%, meaning that more than half the volume is empty space. This high porosity reduces the bulk density far below the intrinsic density of the constituent materials. For comparison, pure water ice has a density around 900 kilograms per cubic meter, and silicate rocks range from 2,500 to 3,500 kilograms per cubic meter. A mixture with 60% porosity and equal parts ice and rock would have a bulk density around 800 kilograms per cubic meter, consistent with the upper end of estimates for 3IATLAS. The internal structure implied by low bulk density affects how the nucleus responds to stresses. Highly porous bodies have low tensile strength, making them susceptible to fragmentation under rotational stresses, thermal expansion, or tidal forces. The survival of 3IATLAS through perihelion, where thermal stresses peak, suggests either that the nucleus is not as porous as the density estimates imply, or that its internal structure provides sufficient cohesion despite high porosity. One possibility is that the nucleus has a differentiated structure, with a denser core surrounded by a lower density mantle. This would increase the effective strength while maintaining a moderate average density. Thermal evolution models explore how heat propagates into the nucleus and drives volatile sublimation. For a porous structure, heat transport occurs through a combination of conduction through solid contacts between grains, radiation across void spaces, and advection by gas flow through the pores. The effective thermal conductivity of such a medium is much lower than solid material, typically in the range of 0.01 to 0.1 watts per meter per Kelvin. This low conductivity means that heat penetrates slowly, creating steep temperature gradients. At perihelion, surface temperatures can reach 200 to 300 Kelvin, while material just meters below the surface remains at cryogenic temperatures below 100 Kelvin. The depth of the active layer, the region where temperatures are high enough to drive significant sublimation, depends on thermal conductivity, insulation, and the sublimation temperature of the volatiles. For carbon monoxide, with a sublimation temperature around 25 Kelvin at cometary pressures, even small amounts of solar heating can trigger activity. Water ice requires temperatures above 200 Kelvin for rapid sublimation, limiting water activity to the uppermost surface layers. The low water abundance in 3IATLAS suggests that the active layer is dominated by more volatile species. Consistent with the observed gas composition and with a subsurface structure where water ice, if present, remains too cold to sublimate efficiently. Collisional history also influences internal structure. If 3IATLAS formed through accretion of smaller bodies in a protoplanetary disk, the resulting structure would be a loosely bound aggregate. If the object experienced collisions during its history, either before ejection from its parent system or during interstellar transit. These impacts could have compacted the interior, increased the bulk density, or created fractures that facilitate gas escape. The lack of clear evidence for recent large impacts, such as fresh craters or asymmetric brightness distributions, suggests that the object has not been heavily processed by collisions since its formation, though smaller impacts below the resolution limit remain possible. Radiation pressure effects. Radiation pressure from sunlight exerts forces on dust particles in the coma, shaping the dust tail and influencing the trajectories of individual grains. The force depends on the grain size, composition, and distance from the sun, with small particles experiencing stronger acceleration than large ones. For particles smaller than the wavelength of visible light, roughly half a micrometer, radiation pressure can exceed solar gravity, causing the particles to accelerate rapidly away from the sun along curved trajectories. Larger particles experience weaker radiation pressure and follow paths closer to gravitational parabolas, leading to a size-dependent separation of dust grains and the formation of dust tails with complex structure. The ratio of radiation pressure force to gravitational force, known as beta, ranges from near zero for large particles to values exceeding 1 for small grains. Beta depends on the particle's absorption and scattering efficiency, which in turn depends on its size, shape, and refractive index. For 3IATLAS, modeling the dust tail morphology provides estimates of the beta distribution and hence the particle size distribution in the coma. The observed tail shape, with a relatively narrow dust tail and a broader fan-like structure, indicates a mixture of particle sizes with beta values ranging from 0.1 to greater than 1, corresponding to grain sizes from tens of micrometers down to tenths of a micrometer. The acceleration profile of dust grains determines how quickly they leave the nucleus vicinity and how the coma density evolves with distance. Small grains with high beta values reach terminal velocities within hours of ejection, while large grains accelerate slowly over days. The terminal velocity, the speed at which radiation pressure balances the gravitational attraction, scales with beta and the heliocentric distance. For beta equals 1 at 1 astronomical unit, the terminal velocity is around 0.6 kilometers per second, increasing closer to the Sun and decreasing farther away. For 3IATLAS, at a perihelion distance of 0.62 astronomical units, terminal velocities for small grains reach nearly 1 kilometer per second, fast enough to clear the inner coma in a matter of hours. Radiation pressure also affects the spatial distribution of dust in the coma. Immediately after ejection from the nucleus, dust grains move radially outward at the gas expansion velocity, roughly 400 meters per second. As radiation pressure accelerates the grains anti-sunward, the trajectories curve, creating a fan-shaped distribution. The opening angle of the fan depends on the initial ejection velocity and the radiation pressure acceleration, with faster acceleration producing narrower tails. Observations of 3IATLAS show a dust tail with an opening angle of a few degrees, consistent with models for moderate radiation pressure on a mixture of grain sizes ejected at typical cometary velocities. The color of the dust tail provides additional information about particle properties. Radiation pressure is wavelength dependent, being stronger at shorter wavelengths where photon energies are higher. This leads to chromatic effects where different colors of light are scattered preferentially by different grain sizes. Small grains scatter blue light more efficiently, while large grains scatter red light. By observing the tail at multiple wavelengths and comparing the brightness profiles, the size, distribution, and composition can be refined. For 3IATLAS, the tail appears neutral to slightly red in color, indicating a dominance of larger grains or a compositional mix that includes organic materials, which tend to be red due to complex carbon chemistry. Polarization measurements offer another probe of dust properties through radiation pressure effects. Scattered sunlight becomes partially polarized, with the degree of polarization depending on the scattering angle, particle size, and particle shape. For 3IATLAS, polarization observations across a range of phase angles show polarization levels around 20 to 30% higher than typical for solar system comets. This suggests that the dust grains are more elongated or have surface roughness that enhances polarization. The polarization measurements, combined with color and brightness data, constrain the grain properties more tightly than any single type of observation alone. Radiation pressure can also drive dynamical effects beyond simple tail formation. For dust grains with very high beta values, radiation pressure can impart enough velocity to unbind the grains from the solar system entirely, sending them on hyperbolic trajectories into interstellar space. These grains become interstellar dust particles, contributing to the population of grains detected by missions like Ulysses and New Horizons. For 3IATLAS, the production of such grains depends on the efficiency of producing very small particles through fragmentation or condensation in the coma. If a significant fraction of the dust consists of submicron grains, the comet could be injecting material into the interstellar medium at rates comparable to or exceeding the mass loss from the nucleus itself. Outgassing asymmetry. The distribution of outgassing across the nucleus surface determines the structure of the coma, the morphology of the jets, and the non-gravitational forces acting on the body. For most comets, outgassing is concentrated on the sunlit hemisphere, driven by solar heating. However, the specific pattern depends on factors like surface composition, topography, thermal inertia, and the rotation state. An idealized spherical nucleus with uniform composition and rotation would produce symmetric outgassing peaked at the subsolar point. Real comets deviate from this ideal, exhibiting jets, fans, and localized bright regions that indicate heterogeneous surfaces and complex heating patterns. For 3IATLAS, the observed jets point to highly localized outgassing sources, possibly associated with specific surface features like fractures, vents, or exposed ice deposits. The jets maintain distinct directions over timescales longer than the rotation period, suggesting that the sources are not simply rotating active patches, but may involve deeper structures that channel gas from subsurface reservoirs. If the nucleus has a network of fractures connecting volatile rich regions to the surface, gas could flow through these conduits and emerge at specific locations regardless of the local surface temperature. This decouples outgassing from direct insolation and allows jets to persist even when their source regions rotate into shadow. Topographic effects can also concentrate outgassing. Depressions, craters, or valleys can trap solar radiation, creating local hotspots where temperatures exceed the surrounding terrain. These hotspots drive enhanced sublimation, producing jets that align with the topographic features rather than with the subsolar point. For 3IATLAS, if the nucleus has significant topographic relief with depth to width ratios greater than 1, meaning deep pits or narrow valleys, the enhanced heating in these features could explain the observed jet activity. Models of insolation in rough terrain show that temperature increases of tens of degrees are possible in favorable geometries, sufficient to shift the sublimation rate by factors of several. The thermal inertia of surface materials influences the timing and duration of outgassing. High thermal inertia materials, like solid rock, heat slowly but retain heat long after local sunset, allowing outgassing to continue into the night side. Low thermal inertia materials, like fluffy dust or frost, heat quickly but cool just as fast, producing outgassing that tracks the insolation closely with minimal lag. For 3I/ATLAS, the observed jet activity shows some phase lag relative to the rotation period, with peak brightness occurring a few hours after the presumed subsolar time. This lag suggests intermediate thermal inertia, consistent with a surface covered by a mix of ice and dust, with particle sizes in the millimeter to centimeter range. Outgassing asymmetry produces torques that can change the nucleus rotation state. If jets are not symmetric about the rotation axis, the reaction force has a component perpendicular to the spin axis, exerting a torque. Over time, this torque can spin up or spin down the nucleus, change the orientation of the spin axis, or excite non-principal axis rotation. For 3I/ATLAS, the measured rotation period shows no significant change over the observation period, implying that the torques average to near zero over each rotation. This could occur if the active regions are distributed symmetrically, if jets from different regions exert opposing torques that cancel, or if the rotation period is already at an equilibrium where outgassing torques balance dissipative damping. The spatial distribution of dust and gas in the near-nucleus region reflects the outgassing pattern. High-resolution imaging, capable of resolving structure within a few hundred kilometers of the nucleus, would show whether the coma has a uniform shell or exhibits jets, spirals, or other asymmetries. The leaked documents referenced such imaging, reportedly showing multiple distinct plumes radiating from the nucleus. If accurate, this confirms that outgassing is localized to a small number of sources rather than distributed across the entire surface. The number of distinct plumes, their orientations, and their time variability provide direct constraints on the number of active regions, their sizes, and their relationship to surface features. Compositional variations between different jets could indicate that different regions of the surface have different volatile inventories. If one jet is rich in carbon monoxide, while another has more carbon dioxide or water, this would point to heterogeneous composition, possibly reflecting different formation conditions or different degrees of processing. Spectroscopy of individual jets, rather than the integrated coma, requires high spatial and spectral resolution and has been achieved for only a handful of well-studied solar system comets. For 3I/ATLAS, the data resolution may not suffice for jet-by-jet composition, but integrated spectroscopy over the rotation cycle could reveal variations that hint at compositional diversity. Gas production mechanisms. The mechanisms that drive gas production from cometary nuclei involve a combination of thermal and non-thermal processes. Thermal sublimation, where solar heating raises the temperature of ices above their sublimation point, is the dominant mechanism for most comets. However, other processes, like sputtering by energetic particles, photodesorption by ultraviolet photons, and chemical reactions can contribute, especially in low-temperature regions or for less volatile species. Understanding which mechanisms operate in 3I/ATLAS and their relative importance helps explain the observed activity levels, composition, and temporal variations. Thermal sublimation of carbon monoxide, the main volatile in 3I/ATLAS, begins at temperatures as low as 25 Kelvin, far below the temperatures needed for water ice sublimation. This means that carbon monoxide can drive activity even at large heliocentric distances where solar heating is weak. The sublimation rate depends exponentially on temperature through the Clausius-Clapeyron equation, with rates doubling for every few degrees of temperature increase. At perihelion, surface temperatures on the sunlit hemisphere likely exceed 200 Kelvin, driving carbon monoxide sublimation rates high enough to produce the observed outgassing. However, the persistence of jets on the night side or in shadowed regions requires either that heat diffuses into these areas or that other mechanisms are at work. Photodesorption, the release of molecules from surfaces by absorption of ultraviolet photons, provides a non-thermal pathway for gas production. Ultraviolet photons with energies above a few electron volts can break the bonds holding molecules to dust, grains, or ice surfaces, ejecting them into the gas phase. This process operates even at very low temperatures and can release molecules from regions that never reach sublimation temperatures. For 3IATLAS, photodesorption could contribute to the observed gas production, particularly for more volatile species absorbed onto dust grains in the coma. However, quantifying the contribution requires knowing the surface area of dust particles, the ultraviolet flux, and the photodesorption yields for different molecules, all of which carry significant uncertainties. Chemical reactions in the subsurface or on grain surfaces can also produce gas. Radiolysis, the breaking of chemical bonds by energetic particles like cosmic rays, can decompose complex molecules into simpler, more volatile species. Over the lifetime of an interstellar object, cosmic ray exposure can process the outer layers to depths of several meters, creating a layer rich in reactive species and volatile fragments. When this material is heated during perihelion passage, the radiolysis products can outgas, contributing to the observed emissions. For 3IATLAS, the long interstellar transit time, likely millions of years, means that cosmic ray processing has had ample time to modify the composition of the near-surface layers. The energy budget for outgassing includes not just the latent heat of sublimation, but also the energy needed to lift material out of the nucleus's weak gravity field. For a nucleus with a mass of 10 to 12 kilograms and a radius of 2 kilometers, the surface gravity is about 0.0005 meters per second squared, giving an escape velocity of around 1.4 meters per second. This is much lower than the thermal velocities of gas molecules at typical sublimation temperatures, meaning that essentially all gas produced escapes into space rather than being gravitationally bound. The low escape velocity also means that dust grains can be lofted easily if the gas production rate is sufficient to overcome cohesive forces holding grains to the surface. Gas expansion from the nucleus surface creates a collisional zone where molecules frequently collide with each other, transferring momentum and energy. This zone extends from the surface to a distance where the gas density drops low enough that collisions become rare, typically a few tens of kilometers for moderate outgassing rates. Within the collisional zone, the gas flow can be described by fluid dynamics, with temperature, density, and velocity fields that vary smoothly. Beyond the collisionless boundary, molecules follow ballistic trajectories, and the coma transitions to a free molecular flow regime. For 3IATLAS, the transition occurs at distances small compared to the observable coma, meaning most of what we see is in the collisionless regime, where molecules have not interacted since leaving the collision zone near the nucleus. The energy balance in the collision zone determines the gas temperature and velocity. As gas expands from the high-density region near the surface into the lower-density coma, it does work against the pressure gradient, cooling adiabatically. This cooling can reduce the gas temperature from the surface temperature of 200 to 300 Kelvin down to tens of Kelvin in the outer coma. The expansion velocity increases as the gas accelerates away from the nucleus, reaching terminal velocities comparable to the thermal velocity at the surface temperature. For carbon monoxide at 200 Kelvin, the thermal velocity is around 350 meters per second, consistent with the observed expansion velocities. Interstellar dust contamination. During its journey through interstellar space, 3IATLAS would have encountered interstellar dust grains, micron-sized particles that pervade the galaxy at densities of roughly 1 grain per cubic astronomical unit. Over millions of years, the cumulative effect of these collisions can erode the surface, implant material, and alter the composition of the outermost layers. The impact velocities, determined by the relative motion between the object and the dust, likely ranged from 20 to 50 kilometers per second, fast enough to vaporize impacting grains and excavate material from the surface. Understanding the extent of this processing helps interpret the observed surface properties and composition. The erosion rate depends on the dust density in the interstellar medium, the object's velocity, and its cross-sectional area. For a nucleus traveling at 25 kilometers per second through a medium with a dust density of 10 to minus 18 kilograms per cubic meter, the mass flux onto the surface is roughly 10 to minus 13 kilograms per square meter per year. Over a million years, this accumulates to about 0.1 kilograms per square meter, or a layer a few millimeters thick if the impacting material were to stick. However, hypervelocity impacts typically excavate more material than they deposit, with excavation to projectile mass ratios ranging from 10 to several hundred, depending on impact, velocity, and target properties. This means that erosion dominates over accretion, and the net effect is surface ablation. The erosion pattern would be non-uniform, with the leading hemisphere facing into the direction of travel experiencing higher impact rates than the trailing hemisphere. This asymmetry creates differences in surface texture, composition, and volatile content between hemispheres. If the rotation axis of 3IATLAS were aligned with the direction of interstellar motion, one hemisphere would be preferentially eroded, potentially explaining some of the observed surface heterogeneity. However, the rotation axis orientation during interstellar transit is unknown and could have changed due to collisions or outgassing torques during previous perihelion passages in its parent system. Chemical alteration from dust impacts adds complexity. Hypervelocity impacts generate high temperatures and pressures, driving shock chemistry that can synthesize new compounds. Organic molecules in interstellar grains, when shocked, can polymerize into more complex species or decompose into simpler volatiles. The implanted material mixes with the target surface, creating a rind of processed material that may differ compositionally from the pristine interior. For 3IATLAS, the low water abundance and high carbon content could partly reflect interstellar processing, with water ice preferentially eroded and carbon-rich organic material from impactors accumulating or synthesizing in situ. Radiation damage from cosmic rays and ultraviolet photons complements the impact processing. Cosmic rays, primarily high-energy protons and heavier nuclei, penetrate to depths of several meters, breaking chemical bonds and creating free radicals and volatile fragments. The timescale for significant damage is millions of years, comparable to the likely interstellar transit time for 3IATLAS. Ultraviolet photons from the interstellar radiation field, though much less energetic than cosmic rays, affect the surface layers to depths of micrometers, destroying some molecules and creating photochemical products. The combined effect of radiation and impacts is a surface that has been substantially altered from its primordial state. The detection of interstellar grain signatures in the 3IATLAS composition would provide direct evidence of contamination. Isotopic anomalies, unusual elemental ratios, or the presence of specific organic compounds characteristic of interstellar material could all serve as markers. The nickel-iron inversion, if not primordial, might result from selective accumulation of nickel-rich interstellar grains. Interstellar dust grains show a wide range of compositions, with some populations enriched in specific elements due to their formation environments, such as supernovae ejecta or circumstellar outflows from asymptotic giant branch stars. Mixing even a small fraction of exotic grains into the surface layers of 3IATLAS could produce detectable anomalies. Laboratory simulations of interstellar weathering involve accelerating dust grains to hypervelocities and impacting them onto ice and rock targets under vacuum. These experiments show that even relatively modest impact velocities, tens of kilometers per second, can cause substantial erosion and mixing. The products include shocked material, vapor, and melt that recondenses onto nearby surfaces. Scaling these results to realistic interstellar exposure durations suggests that the outermost meters of 3IATLAS have been thoroughly reworked, with the original surface composition obscured by the gardening effects of impacts and radiation. Outburst activity analysis. Cometary outbursts, sudden increases in brightness and gas production lasting hours to days, are common phenomena attributed to rapid release of volatiles from beneath the surface. Outbursts can be triggered by thermal cracking of an insulating crust, pressure buildup from subsurface sublimation, or exposure of fresh ice through landslides or structural failure. For 3IATLAS, the light curve and spectroscopic data contain hints of outburst-like events, though distinguishing true outbursts from rotational modulation or viewing geometry effects requires careful analysis. The amplitude and duration of outbursts constrain the physical processes involved. A localized outburst releasing 10 to the 27 molecules over a few hours, for instance, implies a surface area of roughly 1 square kilometer sublimating at high rates, or a smaller area with more intense activity. The energy required to vaporize this much material, accounting for the latent heat of sublimation, is on the order of 10 to the 13 joules, equivalent to the insolation on a square kilometre over several hours at perihelion. This suggests that thermal heating alone could drive such events if conditions are favourable, without requiring exotic energy sources. The trigger mechanisms for outbursts vary. One scenario involves a thin dust mantle that insulates subsurface ice, allowing pressure to build as volatiles sublimate beneath the crust. Eventually, the pressure exceeds the tensile strength of the crust, causing it to crack or blow off, releasing the trapped gas in a sudden burst. This mechanism predicts that outbursts should correlate with solar heating cycles, occurring preferentially when a given region is illuminated for the first time in a rotation period, or when cumulative heating over several rotations finally breaches the critical pressure. For 3IATLAS, outbursts timed to specific rotation phases would support this model. Alternative triggers include structural failure unrelated to pressure buildup. If the nucleus has cliffs, overhangs, or weakly bound layers, thermal expansion and contraction could destabilize these features, causing collapses that expose fresh ice. The newly exposed material sublimates rapidly, producing a brightness increase. This mechanism does not require pressure buildup and can occur at any time when thermal stresses exceed material strength. The lack of correlation with specific rotation phases would favor structural over pressure-driven outbursts. Spectroscopic observations during outbursts reveal whether the ejected material differs compositionally from the steady-state outgassing. If an outburst taps a subsurface reservoir with different volatile abundances, the gas composition should shift during the event. For 3IATLAS, time-resolved spectroscopy around suspected outbursts shows variations in carbon monoxide emission that could indicate compositional changes. Though the data resolution and signal-to-noise ratios are marginal, higher quality observations would be needed to confirm whether outbursts access different material than the background activity. The frequency of outbursts provides information about surface structure and volatile distribution. If outbursts are common, occurring multiple times per rotation period, this suggests that the nucleus has many small active regions, or that the conditions for triggering outbursts are easily met. If outbursts are rare, this implies that either the surface is more homogeneous or that the trigger conditions are restrictive. For 3IATLAS, the available data hint at a few possible outburst events over the weeks of observation, implying a frequency of perhaps one per few rotation periods. This is within the range seen for active solar system comets. The long-term effects of outbursts on the nucleus evolution include mass loss, surface modification, and changes in the rotation state. Each outburst removes material, contributing to the overall mass loss rate. If outbursts are localized, they can excavate pits or craters, roughening the surface topography. The asymmetric mass ejection from outbursts can also exert torques, altering the spin rate or orientation. Over many orbits or perihelion passages, these effects accumulate, shaping the nucleus into its current state. For 3IATLAS, this is its first observed perihelion passage since ejection from its parent system, but the nucleus may have experienced many prior passages that conditioned its surface and interior. Nucleosynthetic signature analysis. The elemental and isotopic composition of 3I. ATLAS carries information about the stellar environment where its parent system formed. Nucleosynthesis, the process by which elements are created in stars and dispersed through supernova explosions and stellar winds, produces specific abundance patterns that vary depending on the mass, metallicity, and evolutionary state of the progenitor stars. The molecular cloud from which the parent planetary system condensed inherited its composition from multiple generations of stars, and this primordial signature should be preserved in primitive bodies like cometary nuclei that never experienced significant thermal processing. The nickel-to-iron ratio observed in 3IATLAS provides the most striking deviation from solar system norms. In the solar system, iron outweighs nickel by factors of 15 to 20 in most primitive materials, reflecting the integrated nucleosynthetic output of the stellar populations that contributed to the pre-solar molecular cloud. This ratio is relatively uniform across different solar system bodies, from carbonaceous chondrite meteorites to cometary volatiles, indicating thorough mixing in the solar nebula. The reversed ratio in 3IATLAS, with nickel exceeding iron, demands explanation through either different nucleosynthetic inputs or selective fractionation processes that concentrate nickel preferentially. Type Ia supernovae, the thermonuclear explosions of white dwarf stars that have accreted mass from companion stars, produce substantial quantities of nickel 5,6 through explosive silicon burning. This radioactive isotope decays through cobalt 5,6 to stable iron 5,6 with a half-life of about 6 days, providing the energy that powers the supernova's optical display. However, the decay occurs after the ejector has expanded and cooled, meaning that the synthesized material enters the interstellar medium as iron, not nickel. Stable nickel isotopes, primarily nickel 5,8 and nickel 6,0, are also produced in these events, but in smaller quantities. The nickel enhancement in 3IATLAS would require that the parent molecular cloud was enriched by multiple recent Type Ia events, or by a different supernova type with unusual yields. Type II supernovae, the core collapse explosions of massive stars, produce both iron and nickel through alpha-rich freeze-out processes in the innermost ejector layers and through explosive nucleosynthesis in the outer layers. The iron to nickel ratio in these ejecta depends on the progenitor star's mass and composition, with some models predicting nickel enhancements in specific mass zones. If the molecular cloud that formed 3I-ATLAS's parent system was contaminated by ejecta from a nearby massive star that exploded shortly before cloud collapse, the local composition could differ from the galactic average. The timing would need to be precise, with the supernova occurring within a few million years of cloud collapse to prevent the ejecta from mixing into the broader interstellar medium. Electron capture supernovae, a rare subclass involving the collapse of oxygen, neon, magnesium cores in stars at the boundary between white dwarf and neutron star formation, produce distinct nucleosynthetic signatures. These events synthesize intermediate mass elements, including enhanced nickel production relative to iron in some models. The frequency of such explosions is uncertain, with estimates ranging from a few percent to perhaps 10% of all core collapse events. If 3I-ATLAS formed in a stellar environment where electron capture supernovae contributed disproportionately to the enrichment history, the nickel-iron anomaly might be explained. Isotopic ratios provide additional discriminating power. Different nucleosynthetic processes produce different isotopic patterns, even for the same element. For nickel, the 5 stable isotopes, nickel 5,8, nickel 6,0, nickel 6,1, nickel 6,2, and nickel 6,4, have varying abundances depending on whether they formed through hydrostatic burning in stellar cores, explosive nucleosynthesis in supernovae, or neutron capture processes in asymptotic giant branch stars. High-resolution spectroscopy capable of resolving individual isotopic lines would reveal whether the nickel in 3I-ATLAS has solar isotopic ratios or shows deviations that point to specific stellar sources. Unfortunately, the spectral resolution and signal-to-noise achieved for 3I-ATLAS are insufficient for isotopic measurements, leaving this critical test for future observations of similar objects. The carbon-to-oxygen ratio offers another nucleosynthetic diagnostic. Carbon is primarily synthesized in helium-burning regions of stars and ejected through stellar winds or supernovae. Oxygen comes from similar sources, but with different production efficiencies depending on stellar mass. The solar system's carbon-to-oxygen ratio reflects a specific balance between contributions from different stellar types. For 3I-ATLAS, the high carbon monoxide abundance and low water content suggest a carbon-rich environment, potentially indicating formation in a system where asymptotic giant branch stars, which can become carbon-rich late in their evolution, contributed more heavily to the molecular cloud composition. Deuterium abundance measurements constrain the temperature and chemical conditions during formation. Deuterium, formed primarily during Big Bang nucleosynthesis, is progressively destroyed in stellar interiors where temperatures exceed 1,000,000 Kelvin. The deuterium to hydrogen ratio in the local interstellar medium is roughly 20 parts per million, depleted from the primordial value by galactic chemical evolution. In molecular clouds, deuterium fractionation enriches deuterium in certain molecules through low-temperature ion-molecule reactions. The degree of enrichment depends on temperature, with maximum fractionation occurring below 20 Kelvin. For 3I-ATLAS, the deuterium to hydrogen ratio in water molecules, though poorly constrained due to low water abundance, suggests enrichment consistent with formation at temperatures below 25 Kelvin, placing the formation zone in the cold outer regions of a protoplanetary disk, or in a prestellar core environment. The nitrogen isotope ratio, nitrogen 1,5 to nitrogen 1,4, is sensitive to chemical processing history. In the solar system, This ratio varies between different reservoirs, with enhancements in some cometary materials attributed to iron molecule chemistry in cold environments. For 3IATLAS, nitrogen isotope measurements would require detection of nitrogen-bearing molecules like molecular nitrogen, ammonia, or hydrogen cyanide, and resolution of isotopic features. The leaked documents mention tentative detections of nitrogen-bearing species, but without sufficient data quality for isotopic analysis. Future observations with higher spectral resolution could access this information. Radioactive isotope abundances, particularly short-lived isotopes with half-lives less than a few million years, provide chronological constraints. Isotopes like aluminum-26, with a half-life of 720,000 years, and iron-60, with a half-life of 2.6 million years, are produced in supernovae and can be incorporated into forming planetary systems if the timing is right. The presence and abundance of decay products from these short-lived isotopes in primitive solar system materials demonstrate that the solar system formed shortly after nearby supernova events. For 3IATLAS, detecting evidence of extinct radioactivity would require laboratory analysis of returned samples or high-precision remote measurements beyond current capabilities. But the nucleosynthetic anomalies already observed hint that the formation environment may have been enriched by recent stellar events. Electric discharge phenomena. Electrostatic charging of cometary nuclei and dust grains creates conditions where electrical discharges might occur, particularly in regions where charge densities build up through photoelectric emission, solar-wind interactions, or triboelectric effects from colliding dust particles. Electrical phenomena on comets have been theorized for decades, but direct observations remain scarce due to the difficulty of detecting transient discharge events remotely and the lack of in situ measurements with appropriate instrumentation. For 3IATLAS, several observed features hint at possible electrical activity, though definitive evidence is absent without dedicated high-time resolution observations or close proximity measurements. Photoelectric emission, the ejection of electrons from surfaces by ultraviolet photons, charges the sunlit side of the nucleus positively as electrons escape to space. The charging rate depends on the ultraviolet flux, surface composition, and work function of the materials. For typical cometary surfaces at 1 astronomical unit, surface potentials can reach several volts positive relative to the surrounding plasma. At 0.62 astronomical units, where 3IATLAS reached perihelion, the enhanced solar ultraviolet flux would drive higher charging rates, potentially reaching tens of volts. The night side and shadowed regions not exposed to photoelectric emission charge negatively through collection of electrons from the plasma environment, creating potential differences across the nucleus surface. Dust grain charging follows similar principles, but with complications due to the grain's small size and mobility. As dust grains leave the nucleus surface, they enter regions where the plasma density and potential vary. The grains acquire charge through electron and ion collection, photoelectric emission, and secondary electron emission from high-energy particle impacts. The equilibrium charge on a grain depends on its size, with small grains charging to lower absolute charges, but higher charge to mass ratios than large grains. For micron-sized grains in the inner coma, charge to mass ratios can reach values where electrostatic forces become comparable to gravity and radiation pressure, influencing grain trajectories. Electrostatic levitation and transport of dust grains can occur if electric fields are strong enough. On airless bodies like asteroids and the Moon, electric fields have been invoked to explain dust ponds, rays, and horizon glow, though direct measurements remain limited. For cometary nuclei, the outgassing creates additional complications, with the gas flow exerting drag forces that compete with electrostatic forces. However, in regions where outgassing is weak or intermittent, such as inactive areas or during the night side of the rotation, electrostatic forces could dominate and move fine dust against gravity. This mechanism might explain the presence of dust hazes or clouds not obviously connected to active jets. Triboelectric charging, where surfaces become charged through contact and separation, occurs when dust grains collide with each other or with the nucleus surface. Laboratory experiments show that insulating materials can acquire substantial charges through repeated contacts, with charge separation occurring because different materials have different electron affinities. In a cometary coma, where dust grains collide frequently in the near nucleus region, triboelectric charging could build up charge distributions that differ from those predicted by photoelectric and plasma collection alone. The resulting electric fields could influence grain trajectories, creating preferential directions for dust, transport, or causing grains to clump together electrostatically. Electrical discharges, analogous to lightning, could occur when potential differences exceed breakdown thresholds. For a vacuum or low-density gas environment, breakdown voltages are higher than in Earth's atmosphere, requiring field strengths of tens of kilovolts per meter over relevant length scales. If regions of the nucleus surface develop opposing charges, separated by distances of meters to kilometers, potential differences could reach kilovolts. Discharge events would produce brief flashes of visible and ultraviolet light, electromagnetic pulses detectable at radio frequencies, and possibly accelerate charged particles to high energies. Detecting such events requires high time resolution, photometry, or radio monitoring during periods of peak activity. Observed brightness fluctuations in the coma of 3IATLAS, varying on timescales of minutes to hours, could potentially be attributed to discharge events, though other explanations like rotating jets or viewing geometry changes are also viable. Discriminating between these possibilities requires multi-wavelength observations with sufficient time resolution to capture transient events. Radio observations at frequencies from kilohertz to megahertz, where discharge-generated electromagnetic pulses would appear, have not been reported for 3IATLAS, leaving this channel unexplored. Future observations of active comets with radio arrays could search for such signatures. Plasma instabilities driven by electrostatic effects might also play a role in shaping the coma and tail structures. If dust grains become charged and gyrate in the magnetic field, they can drive wave modes that affect the plasma dynamics. The dust-plasma interactions create a complex multi-component system where electrostatic and electromagnetic forces couple particles of vastly different masses, from electrons through ions to dust grains, spanning many orders of magnitude in size. Simulations of dusty plasmas in cometary environments show that under some conditions, the system can become unstable, producing organized structures like spirals, filaments, or shells. Whether such instabilities operate in 3I, ATLAS depends on parameters like the dust-to-gas ratio, charging rates, and magnetic field strength, most of which are poorly constrained. The possibility of electrical activity has implications for understanding the jets and their stability. If electrostatic forces confine charged dust grains within flux tubes aligned with electric or magnetic field lines, the jets could maintain narrow widths over long distances without dispersion. The field lines would act as guides, channeling particles along specific directions regardless of the nucleus rotation. This mechanism offers an alternative to purely magnetic confinement and might operate in tandem with magnetic fields to produce the observed jet geometries. Testing this hypothesis requires measurements of the electric field structure in the coma, achievable only with in situ probes carrying electric field sensors and Langmuir probes to measure plasma density and temperature.